Welcome back. So we talked about initialization, notably Javier initialization, and we basically said that we want random initializations such that our weights or each coordinate in our weights and biases are zero-mean random variables independent of each other with a certain strengths. The strength was basically, let's say, inversely proportional to the D in, let's say, plus D out. Okay, and D in and D out are basically the size of the input and output of a specific layer. So what does this mean? If I have a smaller layer, the weights are going to be larger for that compared to a larger layer because the terms in the denominator are going to be smaller. Okay, so therefore we are performing some sort of normalization across all layers. We want to make sure that all the different layers are more or less the same. Okay, despite having different dimensions, different input sizes and output sizes. Okay, but we are doing this normalization only at the initialization time. Okay, so we want to make sure that the weights, the layers are again more or less the same at initialization. Okay. However, as we are updating the weights, we may lose this normalization idea. Okay, so the weights gets updated, the weights will change, and therefore the strengths of each layers are going to change. Okay. Therefore, there has been some ideas in the literature to, I would say, extend what we talked about, okay, the normalization at initialization, to normalization throughout training. Okay, and we're going to talk about a couple of these ideas. Okay, so a couple of these normalization ideas. Again, the idea is that we want to extend this normalization of the outputs throughout training. We don't want to just do it at initialization. There is a nice connection, I would say, at least intuitive connection to adaptive training methods that we're going to talk about later on in this course. And the idea is in those algorithms is also very similar. So we are performing some normalization to make sure that the parameters are basically getting updated more or less with the same rate. Okay. All right. So I would say normalization ideas are not well understood, despite being very effective. But there have been some studies from the perspective of optimization, actually, to try to understand why normalization is effective. So a number of these studies suggest that when we are normalizing activations, okay, this could lead to a smaller gradients. Okay, and if you recall from the theorems we discussed in the beginning of the course, we said that, let's say, the convergence of gradient descent was proportional to the Lipschitz constant, okay, or the smooth constant. So the larger the Lipschitz constant or the smooth constant, the slower the convergence. The larger the sensitivity of our function, the more careful the algorithm has to be. Therefore, it has to use, let's say, a smaller step size, and the convergence will be slower. Okay. Now, normalization could lead in certain scenarios, not in all scenarios, to a smaller gradient. Therefore, what is happening is that effectively we are lowering the Lipschitzness and the smoothness parameter of our loss function. So we are improving the landscape of the loss. Therefore, we could be able to converge faster. And in terms of generalization and test accuracy, there is also some studies connecting the sharpness of the loss landscape to bad generalization. Okay, so therefore, if by normalization we are reducing the sharpness and sensitivity of our loss, not only we expect the model to converge faster, but also the solution that we're going to find could potentially generalize better as well. Okay. All right, and in the literature there are, I would say, different normalization ideas proposed. here I'm showing 4 of these, but I'm going to talk about batch normalization and layer normalization very briefly. Okay, so what I'm showing here, so basically imagine that you have a batch of samples or a batch of vectors, in particular n vectors or n matrices. Okay, so each matrix is of size h times p, h times w. So this is what I'm going to call p. So p is basically the product of h and w. Imagine that again you have like a image, 2-dimensional input, and you are vectorizing that. Okay, and you could also have like different channels. For instance, an RGB image has 3 channels. Okay, but in the derivations or discussion in the next slide, I'm just going to assume c is equal to 1. Okay, so for us in our discussion, we just assume c is equal to 1. Okay, now what does batch normalization do? So batch normalization basically is doing normalization. It's doing that normalization across the batch of these vectors. Okay, so we are doing some sort of averaging, let's say, and normalization in this direction. Layer normalization, on the other hand, it performs basically a normalization in another direction. It does so in this direction. Okay, so let's talk about this. All right. So as I said, we're going to consider a batch of vectors. Let's say the batch is calligraphic B. We have capital B vectors. Let's call them U1, UB. So these are basically the activation vectors associated with the data points we are processing, let's say, in a specific iteration of SGD. Again, remember, mini-batch SGD samples a bunch of data points and then calculates the gradient. Now, the gradient or the stochastic gradient itself is a function of the activation vectors. Okay, so think of this as gradients or activation vectors, basically. And as I said, these are p-dimensional vectors. In the previous figure, p was basically the product of the height and width of let's say, a 2-dimensional input, let's say an image. Okay. So these are basically the activations associated with the samples that we are using in a specific iteration of mini-batch SGD. Now, what's the batch normalization operation? Again, it performs normalization across the batch. Okay, so and it does so in a data-driven manner. So here's the batch normalization operation. We take basically a vector u and we normalize it. Okay, what does that mean? We're going to subtract some mean from it, and we're going to divide by the standard deviation. Okay, given that the standard deviation could be small, we typically, let's say, add a very small constant kappa to ensure that we are performing a numerically stable operation, and we are avoiding division by 0. Okay. But in addition to subtracting the mean and dividing by the standard deviation, we also have 2 parameters here. We have this parameter beta, which is basically a vector, and alpha here, which is also a vector. And alpha and beta are learnable parameters. So we are learning them from the data. As we are updating the parameters of the neural network, we are also update alpha and beta. Okay. This operation is basically the coordinate-wise product. So this basically means that I take the first coordinate of alpha and multiply it with the other vector. Take the second coordinate of alpha and multiply it with the second coordinate of the other vector, and so on and so forth. Okay. So as I mentioned, mu and sigma are basically the mean and the standard deviation across the batch. Okay. So more specifically, or formally, mu b is basically the average of all of these vectors in the mini batch I'm considering, and sigma square, or the variance, is basically the empirical variance, okay, or the sample variance. All right, so this is essentially the batch normalization operation, okay. And now there are some considerations here. So, and I would say most of these are based on the empirical observations we've had. So one observation we've had is that we need this B to be of moderate size, okay? So in particular, if B is small, we're going to suffer loss of information. And if B is large, we're going to incur a lot of computations, okay? So every time we have to, let's say B is the entire data set, right? So every time we have to perform these operations for a very large number of vectors, and this is very, very costly. Therefore, we basically want to find a sweet spot between like small and large batch sizes. So we typically settle for moderate batch sizes. There's also one reason that we want the batch size to be of moderate, and the idea is that sometimes when you are optimizing parameters of neural networks and performing training, noise is going to be useful. So injecting some noise, even intentionally, could be useful, not only for the purpose of improving the training process, but sometimes also in terms of improving the generalization performance of a model, okay? And this is something we're going to talk about a little bit more in our lecture on regularization, okay? So in this case, when the batch size is moderate, therefore our operation is going to be somewhat noisy as well. So this noise could be associated with better generalization that we typically see from the models that employ batch normalization. Okay. All right. So now one question is that how do you actually use it in practice in conjunction with other operations? So here is the idea. Again, consider our multi-layer perceptron model. So we have W, the weight matrix, times X plus P. So this is going to be some vector for each X. And let's say we have, again, a batch of these vectors because we have, let's say, a batch of, let's say, 64 data points that we are processing. So we feed this to batch normalization, okay, and we get a single vector. We feed that to our nonlinear activation function, let's say ReLU. And then we may optionally also feed that to another layer dropout that we haven't talked about that now, but we will in our lecture on regularization. Okay, so this is basically how we implement batch normalization. Okay, now doing the inference basically means that once the training is done and we want to actually use our model, we're gonna do a slightly different thing. So essentially, instead of using the statistics of the, let's say, the batch that I'm going to process during inference, I'm going to actually use the statistics of the entire training data to calculate the mean and the variance of each layer. Okay, so the idea here is that we need that noise during the training to make sure we find a good generalizable solution, but during inference we want to be as accurate as possible. So therefore we want to make sure that we are calculating the mean and variance of the entire training data. Okay, obviously this is going to be quite exhaustive, so calculating the mean and variance over a very large data set. So therefore what we may do in practice is to actually estimate the mean and variance of associated with the statistics of the entire training data during training. Okay, so in particular we can consider these moving averages, right? That are constructed based on the mini batches that we are encountering during training. Okay, so therefore, as the training is done, these averages could be thought of as a good estimator of the entire data statistics. Right, so this is basically batch normalization. Again, the idea is that we are performing some sort of normalization over a batch of vectors. Layer normalization, on the other hand, normalizes each vector individually. Okay, and that's a deterministic operation. It doesn't depend on any statistics. It doesn't depend on the specific batch, which is typically chosen at random. So how do we do this? Again, it's a normalization. We subtract the mean and then we divide by standard deviation. So let's imagine that I have a specific vector u, again like some activation vector. I'm going to calculate the mean of the coordinates of this vector. Therefore, this mean is now going to be a scalar as opposed to the mean vector that we found in batch normalization. We're also going to calculate the variance, so sigma square, or in the empirical variance. And then we're going to perform the normalization. I take my vector, and then I subtract from it mu, this is scalar, times the vector of all ones, divide by a standard deviation, again plus some constant kappa, which is very small, and it's there to ensure we are not avoiding by 0, and therefore our operation is stable. Okay, so this lane normalization is actually proposed to deal with some of the issues people have been facing when trying to implement batch normalization with recurrent neural networks. It also has some benefits. In fact, one benefit of this is that it's going to lead to stabilizing the training because it is an almost scale-free operation. Meaning that if I take my input u and multiply it by alpha, I'm basically also multiplying the mean and the standard deviation by alpha as well. So therefore, the output is not going to change. Okay? So it is very effective in terms of making our operation scale-free, and it's a very useful property that could be attributed to stabilizing this training. Okay. Now, as I mentioned earlier, so in this context we introduce batch normalization and linear normalization for vectors. In practice, we are actually normalizing or dealing with matrices and tensors, right? So nonetheless, we can apply these ideas to quantities that are not necessarily vector. For instance, image-like quantities that could have multiple channels. Okay. So again, this is a picture to have in mind. Batch normalization. We have a bunch of matrices, and we are performing normalization across the batch. But for layer normalization, we are actually normalizing each image individually. All right. So this is basically our discussion on initialization and normalization, two very effective techniques to ensure that our models avoid vanishing gradient and exploding gradient problems. Therefore, we have effective and stable training. So in the next lectures, we're going to talk about a couple of other training techniques and heuristics that we use when we want to optimize parameters of deep brain models. I'll see you next time.